In this video, we will be looking at section 4.4, which covers logarithmic properties. In the last section, we saw three of these. So we saw inverse properties, which said log base b of b to the x is equal to x, and b raised to the log base b power of x, log base b of x is equal to x. We saw Amanda's favorite log rule, which is also known as the exponential property, that says log base b of a to the r is equal to r times log base b of a. And then the change of base formula, which says log base b of a is equal to log base c of a over log base c of b. The two new ones this section are going to be the sum of logs and the difference of logs properties. If we have two logarithms added together with the same base, then we can combine them via multiplication inside a logarithm with the same base. So log base b of a plus log base b of c is equal to log base b of a times c. The difference of logs property says log base b of a minus log base b of c is equal to log base b of a divided by c. So if you have two logs added, you can combine them via multiplication. If you have two logs subtracted, you can combine them via division. So we're going to start by using these properties and just seeing what we can do to simplify them. So first up we have log base 3 of 32 minus log base 3 of 4. These two are subtracted, which means when I combine them into 1, there's going to be division. So that'll give us log base 3 of 32 divided by 4. Wait a minute, 32 divided by 4, that's 8. So this simplifies into log base 3 of 8. Next up, we're looking at 1/2 log base 5 of 36. This one may not seem like it can simplify at all, but we can use Amanda's favorite log rule in reverse. Because we have a coefficient out front, we can pop it up as an exponent. So this is log base 5 of 36 to the 1/2 power. But if something is raised to the 1/2 power, that's the same thing as taking the square root of it. And we know what the square root of 36 is. That's 6. So this simplifies into log base 5 of 6. Next up, we're looking at the log of 12x to the 4th minus the log of 4x. They are subtracted, so I'm going to divide. We get log of 12x to the 4th over 4x. And if I reduce what's in the parentheses, I get log of 3x cubed. Next up, we're looking at 3 log of x plus 2 log of x squared. I can't combine these with multiplication until I handle these coefficients out front. So like I did back with the 1/2, I'm going to pop those up as exponents. So this will give us the log of x cubed plus the log of x squared squared. But x squared squared is x to the 4th. So what we have is the log of x cubed plus the log of x to the 4th. If I combine those with multiplication, x cubed times x to the 4th is x to the 7th. So this simplifies into the log of x to the 7th power. Finally, we've got 2 log of x plus 1/3 log of y minus the log of z. First things first, I'm going to move the coefficients up into exponents. So we are looking at the log of x squared plus the log of y to the 1/3 minus the log of z. These two are added, so they're going to get multiplied together when I put them together. We'll have the log of x squared y to the 1/3. This log of z is subtracted, so I need to divide by that one. So the z goes in our denominator. Using properties of logs is going to help us with solving logarithmic equations later. So make sure you get some practice using these and make sure you're starting to memorize which laws to use where and how they work. So last time what we were doing was condensing logarithms by putting them together. Now we're going to go the other way and expand. So expand each expression so there are no remaining exponents. This first one looks a lot like the last one we did on the last slide. So since the a and b are multiplied, this will be the log of a to the 4th plus the log of b to the 9th. But the c to the 12th is in the denominator, which means we're dividing by it. That means I need to subtract the log of c to the 12th. But it doesn't want any exponents remaining, so I'm going to use Amanda's favorite log rule on each of these to write it as 4 log of a plus 9 log of b minus 12 log of c. Next up, we're looking at log base 3 of the square root of 5x cubed. Now I know this one looks a little bit funny, but you'll have to remember that square roots can be written as a power of 1/2. So we can rewrite this as log base 3 of, we are taking our 5x cubed and raising it to the 1/2 power. Then I can take this 1/2 power and put it out front. So we get 1/2 log base 3 of 5x cubed. Unfortunately, we can't take that exponent out front. We're just going to leave it like that. Finally, we have the natural log of x to the 4th times the 9th root of y to the 8th. So because these two are multiplied in here, I'm going to add them separately. So this is the natural log of x to the 4th plus the natural log of the 9th root of y to the 8th. We need to deal with this 9th root of y to the 8th. So we have to be a little bit more careful about how we notate our radicals. If we are taking the pth root of r to the q, I know that's not really the best notation there, but this is r raised to the q over p power. So that means our 9th root of y to the 8th is equal to y to the 8/9 power. So I can rewrite this expression as the natural log of x to the 4th plus the natural log of y to the 8/9 power. Now if I bring my exponents out front, I've got 4 natural log of x plus 8/9 natural log of y. All right, now that we've got a little bit of practice in using these properties, we're going to see if we can solve a couple of exponential equations. First up, we have 2 raised to the power of 2x minus 5 equals 7 raised to the power of 3x minus 7. I'm going to pull out an extra sheet of paper. And we've got 2 raised to the power of 2x minus 5 equals 7 raised to the 3x minus 7. So you may remember from the previous section that our first step in solving exponential equations was to get the exponential by itself if we could. Now in this case we can't because we have an exponential on both sides, so we can't really help that. But our next step was to take the log of both sides. I'll do the natural log just for funsies. So the natural log of 2x minus 5 is equal to the natural log, oh sorry, I forgot. This is 2 raised to the power of, natural log of 2 raised to the power of 2x minus 5 is equal to the natural log of 7 raised to the 3x minus 7. Now all of those properties of logarithms that we have are going to come in handy. I'm going to bring my exponents out front so that I have 2x minus 5 times the natural log of 2 is equal to 3x minus 7 times the natural log of 7. Now there's no way to get all the x's on one side right now, so I'm going to distribute. This natural log of 2 can get distributed to the 2x and the negative 5. My natural log of 7 can get distributed to the 3x and the negative 7. So I'll have 2x times the natural log of 2 minus 5 times the natural log of 2 is equal to 3x times the natural log of 7 minus 7 times the natural log of 7. Now I need to keep in mind my goal is to get the x by itself. So I need to find all the terms with x's in them, get them on the same side. Everything without an x, this guy and this guy, need to go on the other side. So what I'll do is I will move my 3x natural log of 7 to this side by subtracting it. And then I will move my negative 5 natural log of 2 to that side by adding it. So that will give me my 2x natural log of 2 because that didn't move. I'm subtracting 3x natural log of 7 from both sides. That'll be equal to, I'm adding this guy over, 5 natural log of 2. And we didn't move this one, so it's just chilling here with the minus 7 natural log of 7. On the left-hand side now, both of my terms have an x, so I can factor out x as the greatest common factor. What that leaves me with in parentheses is 2 times the natural log of 2 minus 3 times the natural log of 7. I'm not changing the other side. 5 natural log of 2 minus 7 natural log of 7. Now this is x times stuff equals something. If I divide both sides by stuff, then the x will be by itself. So x is equal to 5 times the natural log of 2 minus 7 times, the natural log of 7 over 2 times the natural log of 2 minus 3 times the natural log of 7. Now I know there are a lot of steps here, but just as with every other equation, since we are solving it, we can check our answer. What I'm going to do first is figure out what this x actually looks like. So we have in the numerator 5 times the natural log of 2 minus 7 times the natural log of 7, close my numerator, divided by 2 times the natural log of 2 minus 3 times the natural log of 7. So that is what x is as a decimal. I'm going to store that as x. So I'm going to go STO, and I'm going to store it as x. And then I'm going to check it in my original equation. 2 raised to the power of 2x minus 5 is that number, which you can see. 7 raised to the power of 3x minus 7 is the same number. So we found the right value of x. It is a lot of steps, but you know how to do all of them. Because when we started, we took the logarithm of both sides. We used the exponent property to where we can bring the exponents out front. We distributed. We moved some terms around. We factored, and we divided. You know how to do all those. It's just a matter of remembering what comes next. And when you're working through these, just keep the goal in mind. I'm trying to solve for x, so what do I need to do to get x by itself? We're going to try this next one. So we have 20 times 1.07 raised to the z power is equal to 8 times 1.13 raised to the z power. Looking at that, it looks a little bit scarier than the last one because we don't just have the exponential expression on each side, we also have these numbers out front. Now there's like 100 different ways to get to the answer, but when I look at this, what I see is I have numbers on both sides, and I could make this at least a little bit simpler if I were to divide both sides by 8. That way, I don't have the extra number on the right. I only have it on the left. 20 over 8, I can divide the numerator and denominator both by 4, and I get 5 halves times 1.07 raised to the z power is equal to my 1.13 raised to the z power. So now I can take the log of both sides and solve from there. So I will have the log of 5 halves times 1.07 raised to the z is equal to the log of 1.13 raised to the z. Now this side, I have multiplication going on. So that means I can break this into two logarithms added together. I have the log of 5 halves plus the log of 1.07 raised to the z. And I haven't touched the right-hand side. The log of 1.13 raised to the z. Now I can take my exponents out front. So this log of 5 halves isn't changing. Plus, I'm going to bring my z out front. So we get z times the log of 1.07 is equal to the log, I'm bringing my z out front. Z times the log of 1.13. I want everything with a z on one side, everything without a z on the other. These two have z's, this one does not. So I'm just going to subtract this guy over to the other side. That'll leave me with the log of 5 halves is equal to z times the log of 1.13 minus z times the log of 1.07. Now since both terms on the right-hand side have a z, I can factor it out. So I have the log of 5 halves is equal to z times the quantity of the log of 1.13 minus the log of 1.07. And then to solve for z, I need to divide by this stuff. And I get z is equal to the log of 5 halves divided by the log of 1.13 minus the log of 1.07. And that's what we get for z. So these exponential equations can definitely be long. They take some time. Just be careful in the steps that you take. Watch your signs. That's all going to be important. Next up, we're going to solve some logarithmic equations. So we were working with exponential equations and logarithms showed up. I wonder if any exponents will show up when we're solving logarithmic equations. So first up, we have log base 3 of 2x plus 4 is equal to 2. If you are ever totally lost and you just don't know what to do with a problem in this section or this chapter, try switching forms. So right now we're in logarithmic form. Let's try putting it in exponential form. That'll give us 3 squared is equal to 2x plus 4. But 3 squared is 9. So we have 9 is equal to 2x plus 4. If I subtract the 4, then 5 is equal to 2x. Dividing by 2, x is equal to 5 halves. And that's our first answer. For the next one, we're looking at 4 times the natural log of 5x plus 5 is equal to 2. Now I can't switch forms until that logarithm's by itself. So I'm going to subtract the 5 over. That will give us 4 times the natural log of 5x is equal to -3. I can divide both sides by 4. So the natural log of 5x is equal to -3/4. Now the logarithm's by itself, so I can switch this to exponential form. I don't see a base, but it's a natural log, so my base is e. So I will have e raised to the -3/4 power is equal to 5x. And to solve for x, I divide by 5 on both sides. We get x is equal to e to the -3/4 power over 5. And that's a perfectly acceptable answer. Moving on to this third equation, we have the log of x plus 5 minus the log of x plus 2 is equal to 2. The first thing I notice is that I have two logarithms subtracted, and one of our properties of logarithms allows us to combine those as long as we are dividing. So when these combine, I get the log of x plus 5 over x plus 2. And I haven't changed the right-hand side, that's just 2. Now I have the logarithm by itself, so I can switch this into exponential form. I don't see a base, but it's just log. That's a common log that has a base of 10. So if I put this into exponential form, I will have 10 squared is equal to x plus 5 over x plus 2. But we know that 10 squared is equal to 100. So we have 100 is equal to x plus 5 over x plus 2. Now I need to solve for x. I can multiply both sides by x plus 2, or if you like to think of 100 as 100 over 1, then we can cross multiply. We get 1 times x plus 5, which is just x plus 5, is equal to 100 times x plus 2. I'm going to distribute, so I have x plus 5 is equal to 100x plus 200. I'm trying to solve for x, so I'll put all the x's on one side, everything else on the other. I'll subtract the x over so that I have 99x on this side. I'll subtract the 200 over so I have a -195 over here. Dividing both sides by 99, you get x is equal to a -195 over 99. Final one, we have the log of x plus 15 is equal to the log of x plus the log of 15. This is where you have to be really careful with your properties, because which one do you change? This side has two of them added together, so I can combine them using multiplication. We will have the log of x plus 15 is equal to the log of x times 15, which is 15x. If the log of this equals the log of that, then this better equal that. We have x plus 15 is equal to 15x. I can subtract over x, so that 15 equals 14x. Dividing by 14, we get x equals 15 over 14.